The following program is brought to you by Caltech.
Okay, so let's start the afternoon session. The first speaker of the afternoon session is McAllister from Cornell, and he will tell us about ultraviolet completions of large field inflation. Please.
Thanks, Hiroshi, and thanks to the organizers for inviting me. It's a privilege to be able to speak at this meeting, which is very timely. And I'd also like to start out by congratulating the BICEP team on their beautiful and tremendously impressive measurement that's been such an inspiration to the rest of us. I'll be talking about some work. The recent work I'll be describing is represented in this paper with my student Thomas Bachlechner and Mafalda Diaz and Jonathan Fraser, and also some work to appear with my student Cody Long and Paul McGurk. I'm actually going to cover much of the same ground that you heard about in the lovely talks by Andre and Eva, but hopefully in a way that's different enough to be usefully informative. So the motivation for studying high-scale inflation in string theory will form the primary part of the first half of the talk. I'll discuss in quite a lot of detail the symmetry arguments underpinning large field inflation in field theory and in string theory. And then I'll turn to a very brief attempted status report about inflation in string theory. Then I'll talk about a specific class of examples in which the inflaton is an axion field and give some concluding remarks. So the first two sections are really quite general, and then I'll only come to more recent things in part 3. So some things that we've heard before, the amplitude of the primordial gravitational wave signal is set exclusively by the energy scale of inflation. And if you parameterize it in terms of the tensor to scalar ratio, then you find that the energy scale v to the 1/4 is 10 to the 16 GeV times the 4th root of r over 0.1, which it's useful to note is both this scale is approximately the gut scale. It's also 10 to the -2 times the Planck scale. So it's a fantastically high energy. And that's the primary, the initial driver of excitement here. And here's what we, as theorists, can take away from a detection of the imprint of inflationary gravitational waves. So if BICEP has detected the imprint of inflationary gravitational waves, then we learn 3 basic things. One is inflation took place at extremely high energies around the gut scale. We learn that the gravitational field is quantized because those are the fluctuations we are seeing. And then we learned that the inflaton displacement was super Planckian. Any one of these 3 things would be a historic discovery. Any one of them in isolation would be a remarkable window on very high-scale physics, on quantum gravity physics in particular. But we are equipped, it seems, to receive all 3 or none. I'm going to talk mostly about the third one. It's the most subtle of the 3 points. It's also the most informative. We heard a lot about it from Eva in her discussion of the life bound, and I'm going to spell that out a little bit more in the early portion of this talk. One thing to note. Here, this is a 4th root of r appearing. And in this result, for the inflaton displacement, we'll see momentarily that the square root of r appears. I mention those things because for essentially everything in the remainder of my talk, it doesn't matter whether what BICEP has seen is partially primordial and partially dust, or all primordial. A change in the value of r, even down to 10 to the -2, for example, would not substantially change the qualitative findings that I'll be describing. So if there's anything primordial there, all of this goes through. So the life bound is a relationship between the tensor to scalar ratio and the displacement of the inflaton in its field space. So let me illustrate this for slow roll first, for single field slow roll, and I'll discuss how one might try to relax the result by relaxing the conditions of single field slow roll. So in single field slow roll, the scalar power spectrum looks like this in terms of the epsilon parameter, measuring the gradient squared of the potential, and the tensor power is expressed in terms of the energy scale of inflation. So if you manipulate these things, you find that r is equal to 8 times d phi dn. Here n is the number of e-folds in Planck units squared. What that means is the tensor to scalar ratio is effectively related to some velocity squared of the inflaton per E-fold. It's easy to rearrange this, and you get the following result. So far, this is just an identity. It's not a bound of any kind, although the word bound is not a bad one, as I'll explain in a minute. If you're confronted with an expression like this, you don't immediately learn all that much, but if you think you can evaluate this integral in some way, then you can try to estimate how the R that you observe on CMB scales is related to delta phi over M Planck. So another definition, you could define N effective by this relationship here. So R star is the R that's observed on CMB scales. And so if R never changed at all, N effective would be about 60. Whereas if the energy scale of inflation were roughly constant for about 8 E-folds and then dropped dramatically, N effective would be about 8. Okay. Now, the most conservative thing you can assume is that N effective is as small as the number of E-folds over which we actually measure that the energy of inflation is high. So if you measure 2 E-folds worth of gravitational waves, you can say that N effective is about 2. That's a little ridiculous. More realistically, you would say that we have pretty good evidence of very slow variation of some underlying parameters over about 7 or 8 E-folds. So N effective should be at least about 7 or 8. And in fact, in a wide range of very reasonable models, one finds something more like N effective between 30 and 50 or 60. If you put in those estimates, you find that the inflaton displacement is at least R over 0.01 square root. Okay. Now, you can try to relax this result in a bunch of different ways. So I'm going to talk in a couple minutes, although you've already heard it from Eva, about why you might want to try to weaken this statement. Why is it a bound? It's a bound because you've approximated some integral here by integrating over part of the range of support of the integrand. And you've neglected the other part because you don't know it, because we haven't observed those modes. Then, in that sense, it's really a bound. So how can you try and relax it? You could try to violate the slow roll conditions. You could try to change the kinetic term from being a canonical minus a half d phi squared to some p of x, where x is 1/2 d phi squared. Or you could try to introduce additional fields, either at the level of the background evolution or additional fields contributing to the scalar perturbations. And I'm happy to remark on these if anyone's curious, but the short answer is there just aren't any parametrically successful ways of relaxing this relationship. There are a couple of things you can do that will allow you to put, so here I put approximately 1 here. Delta phi over M Planck is greater than or equal to 1 times R over 0.01. You could make the prefactor 0.2 or something like that if you made slow roll be violated shortly after the observed modes exit the horizon. That doesn't change anything qualitative, so it's not a particularly interesting modification. Similarly, you could mess around with the fields that are generating the fluctuations if you have some entropic modes contributing to the perturbations. You can loosen this bound by a factor of 2 or 3 or something like that. It doesn't get you anywhere interesting, so we're really faced with this result. Okay, so why am I perseverating on the life bound? What is it that it tells us that's so interesting? When we write down a scalar Lagrangian in effective field theory, try and write down some inflationary theory like this. So V of phi could be, for example, 1/2 m squared phi squared or something like that, or any of the other inflationary potentials that we've seen so far. What we really have in mind, in the back of our heads, is we're writing down an effective Lagrangian that involves a renormalizable Lagrangian, L here standing for light, L light, phi, plus a sum of irrelevant operators suppressed by some high scale lambda. So you could have a picture in mind. This is just a toy picture where there's one heavy field psi, a cutoff scale lambda, and a light field phi, or maybe several light fields phi. This is measured in terms of energy. And at energies well below lambda, this is a good description. So it'll be very useful for our purposes to introduce the ultraviolet completion of this theory. So here's just a toy model of an ultraviolet completion where I add one field. So I add one heavy field, big psi. And so here, the renormalizable Lagrangian for phi, I've imposed a Z2 symmetry, so it looks just like this. And then I've added a psi kinetic term, some mass for psi, which I'm going to eventually take to be big, and a coupling. Now, if the coupling G vanishes, then nothing interesting comes of the fact that the psi field is present, and these are negligible. So these couplings Ci, the Wilson coefficients, go to 0. On the other hand, if G is of order 1, then the Wilson coefficients are of order 1. if you set this scale lambda equal to the mass scale m of the field you've integrated out. Okay, that's actually going to be important. These are well-known, I think, well-understood things for essentially everybody listening. But the point I want to stress is that whether these terms are present or not depends on whether the light field phi couples or does not couple to heavy modes. It's a question not about existence of heavy modes, but of couplings to heavy modes. So in the case that the light field does couple to heavy modes, what you generally expect is if there's some cutoff scale lambda representing the mass of heavy stuff, then on scales of order lambda in the field space, you find structure in the potential, represented, for example, by higher dimension contributions to the potential term. But also you find structure in the metric on field space. So in the Kahler manifold in the supersymmetric examples we'll encounter. So here the kinetic term receives corrections which are also proportional to powers of phi over lambda. And so when phi changes by an amount that's large compared to lambda, you expect the kinetic terms to change by a large amount. And for example, go from being well-behaved to being ghosts. So the whole Lagrangian changes, not just the potential. That's important to keep in mind. So this is the general expectation. But it's not what a detection of inflationary and gravitational waves would tell us, right? If you see primordial gravitational waves, then you know that the potential varies smoothly over super-Planckian distances. You don't know that it's a simple monomial, but you know that slow roll is unbroken over a super-Planckian displacement. On the other hand, we've seen that in an effective field theory in which the light field, the inflaton field phi, has order 1 couplings to the degrees of freedom of the UV completion, you get structure on scales of order the cutoff. And you can't just make the problem go away by saying, well, I'll just take the cutoff to be much larger than the Planck scale, because gravity behaves badly already at that scale. So GR breaks down at or below the Planck scale, and the or below is important. It can break down a lot below the Planck scale if what you have is actually a parametrically controlled UV completion of gravity, like string theory at weak string coupling and large volume. Then you've got lots of states coming in to your theory at masses that are parametrically below the Planck mass and introducing structure at distances that are parametrically less than Planck scale. So we have to actually grapple directly with the UV completion. And in a sense that I've hinted at already, and I'll make precise in the next couple of slides, detecting inflationary gravitational waves would tell us that the inflaton is weakly coupled to the degrees of freedom that UV complete gravity. Okay, that means that in the context of this grossly oversimplified toy model, if the inflaton potential doesn't have structure over super-Planckian distances, then the UV completion degree of freedom here, psi, must have a weak coupling strength to phi. Remember, if I take this g to 0, then all of these couplings go away. So there's another way of saying that, though, of saying that, making the statement that some light field, the inflaton, is weakly coupled to the degrees of freedom of a UV completion. You can say the light field, the UV completion enjoys an approximate shift symmetry under which the inflaton field shifts. Again, going back to this toy model, if g is equal to 0 and you set the mass and quartic coupling of phi to 0, then phi has an exact shift symmetry. And then even in the absence of a mass and quartic coupling, phi goes to phi plus constant is not a symmetry in the presence of these couplings. Okay, so how does this play out in the context of inflationary model? So Andre showed long ago that if you write down a renormalizable Lagrangian like this, with a canonical kinetic term and some monomial potential, you could imagine p is equal to 2, or we could study some other value of p. It doesn't have to be an integer, but let's take p to be positive. And you imagine, for the moment, neglecting all the non-renormalizable corrections to this theory. You just look at the renormalizable theory. Then, as we heard in the talks by Andre and by Eva, this theory enjoys an approximate shift symmetry, and that shift symmetry renders the theory radiatively stable. In particular, in the limit that you take this mass parameter mu to 0, there are no corrections at all. Now, radiatively stable means, to belabor it, means safe from loops of the light fields. And what are the light fields? The inflaton. So if you set mu to 0, then there aren't any problematic couplings of the inflaton to the inflaton. And the graviton. And you also should be worried about gravitational loops because, of course, GR is not UV complete by itself, so there should be some divergent corrections. But one can estimate how those turn out, and if V itself is small in Planck units, and V double prime is small in Planck units, where prime is a derivative with respect to phi, then those corrections are also small. And so this whole structure here is consistent as a low energy theory if I start out taking all the CIs to be 0. Okay. Now, the burning question is whether the structure admits a UV completion. The theories we're working with here, in particular GR, are not UV complete. So we have to add other degrees of freedom of some kind. And what we'd like to know is what are the effects, not of the loops of the light field, which we already understand here, but what are the effects of the heavy fields, the degrees of freedom of the UV completion. So in string theory, these are, in particular, string states. But they could be more general things. So back to this toy model, we'd like to understand when we introduce fields that can UV complete gravity, how must the inflaton couple to them? And a way of rephrasing this is, does the UV completion approximately respect the low energy shift symmetry? Okay. So I'm going over this again and again because it's really crucial to understand that there is a difference between saying that a model is natural in view of an approximate low energy shift symmetry and saying that the model is perfect, complete, and self-contained. Okay, and to really understand whether a model makes sense in full, you would like to know whether the low energy shift symmetries that make the model work are actually compatible with quantum gravity. Why is there a question at all? I mean, you might ask, do we really have to work it out? Why don't we just assume that there must exist some quantum gravity theory that manifests the desired symmetries? I think that's missing an opportunity. It's missing the opportunity to confront ideas about quantum gravity with experiments. Right? We're missing out on a chance to learn by just assuming away a problem. And we assume away a problem because it's a little bit of work to deal with it, to think about the symmetry structures in quantum gravity, but that's where we can actually make progress. The reason for thinking that not every UV completion will automatically have all the symmetries you want is a very general argument that says that exact continuous global symmetries, with a couple of caveats, are absent in quantum gravity. And that means that all continuous global symmetries have to be approximate symmetries broken at some level. And you could ask, what's the scale of the breaking? So the general expectation, this is not, in most cases, a precise calculation, although the latter half of the talk will amount to a string theory calculation of this, is that the scale of the breaking is around the Planck scale. So that means that the approximate global symmetries that one can achieve in quantum gravity theories allow smooth behavior over about of order 1 m Planck, but not many Planck units. So we'll have to test that directly in string theory. One shouldn't read too much into this lore. This is really just telling you it's a UV-sensitive question. You ought to do a real calculation. So I'll take you to a real calculation. Now, just I have to remark, here's some bizarre things about this, like if we detect inflationary gravitational waves, that's a problem for EFT. That's crazy. It would be like saying that you have a problem for hydrodynamics if you detect evidence that water is composed of water molecules. You know that there's a UV completion underlying whatever effective field theory you're working with. And it shouldn't be surprising if some observables actually depend on the nature of the UV completion. Look, irrelevant interactions are not negligible interactions. They're just generally small at low energies, but they can matter. Eva gave the nice example of melting of a solid as a case which has a very dramatic UV sensitivity. So, moreover, these highly UV-sensitive quantities are our primary opportunity. From the viewpoint of string theory, this is the real chance to learn something about the nature of fundamental physics, the nature of gravity, through cosmological experiments. So we shouldn't miss it by just ignoring the problem. So how do you avoid ignoring the problem? So inflationary gravitational waves, if we can have a totally convincing detection of that, and by the way, of course, it bears stating that an unambiguous detection of primordial gravitational waves is not an unambiguous detection of inflationary gravitational waves. It's just plausibly a detection of inflationary gravitational waves. We'd have to exclude non-inflationary alternative explanations for primordial gravitational waves. So if we see inflationary gravitational waves, we can actually probe the symmetry properties of quantum gravity, provided that we actually, really, legitimately embed inflation in quantum gravity. Not just paying lip service to probably there exists a UV completion, but really trying to run up against the problems that come from the UV completion and see what we learn when we run into those walls. So just to recap briefly, you can easily write down radiatively stable low-energy effective theories that support large field inflation. And the essential structure is an approximate shift symmetry. whose leading breaking comes from the inflaton potential itself. This is the structure you heard about in the 2 preceding talks. And there are 2 canonical intertwined examples. One is chaotic inflation with a monomial potential. For example, m squared phi squared or mu cubed phi or something like that. And the other example connected to it is natural inflation, the cosine potential, which we'll discuss much more. And so the question really for the remainder of the talk is, what kinds of ultraviolet completions do these low energy theories admit, and what do we learn from ultraviolet completing them? So this brings us to inflation in string theory because this is our only available framework right now for actually computing inflationary effective Lagrangians from some sort of quantum gravity structure. So the response of string theorists to the bicep discovery was sort of like this. If you remember Apollo 13, there's sort of an effort to pull out all of the tools we had and see what we could achieve based on an immediate and urgent target. Now, many of us, of course, have been thinking about inflation in string theory for quite some time. The subject has grown actually quite large, but what I think is quite clear, this is evident, I think, in Andre's talk, is that the renewed impetus coming from experiment can guide us to focus much more on specific classes of questions than we had done previously, and that's an exciting opportunity. So what do we actually do if we try to build a model of inflation in string theory? Ideally, what you would do is you would start with a compactification. So it's really an end-to-end calculation. What would you want to do? You'd want to start with a compactification that you specify topologically. You give some topological data of the geometry, wrapped branes, quantized fluxes, et cetera. And then you would derive order by order in a systematic expansion in the 2 fundamental expansions of string theory, the alpha prime expansion and the string loop expansion, a 4-dimensional effective field theory. And you would calculate in that 4-dimensional effective field theory all of the Planck-suppressed, non-renormalizable corrections that we were discussing previously that appear so dangerous. You would actually just compute them. And all of the Wilson coefficients, Ci, that I was writing down, the prefactors of those irrelevant interactions. So in expressions like this, you would compute the structure of those operators, you would compute the scale lambda, and you would compute the Wilson coefficients. Well, that's a long ways away. We can actually do some of that. It's usually pretty easy to identify the scale. In some cases, we've worked out all of the contributing operators. Calculating the Wilson coefficients is quite hard, but sometimes you can estimate them fairly effectively. And it should be borne in mind, this is not a particular problem of string theory. It often happens that you have some ultraviolet completion that's just very hard to work with, and you have to parameterize your ignorance of how the calculation of the effective theory would have worked out if you'd actually been strong enough to integrate out the massive degrees of freedom. I'm talking about a case where you have a perfectly specified UV theory, you know everything about it, except you can't compute very well in it. Then you can't actually do the path integral over the heavy modes and get the IR theory. You just try and guess, right? And often we're driven to much the same thing in string theory. So this is not easy. One of the reasons the problem is difficult is that it relies on corners of string theory which we understand qualitatively, but which are almost orthogonal to the areas where the theory is most amenable to pencil and paper progress. We have the easiest time generally with a lot of supersymmetry and in non-compact geometries or geometries with a lot of symmetry. And the configurations of interest for inflation are non-supersymmetric because positive vacuum energy breaks supersymmetry. They are compact because you need a finite Newton constant. And they're not generally very symmetric. So a lot of our basic tools that have been the underpinning of many of the most beautiful and, in a sense, clean results in string theory are just not immediately applicable to this problem. So that's potentially frustrating. Just to get a sense of the scale of the problem, just to start it out, you would like to solve, suppose you're considering a Calabi-Yau compactification. How do you formulate the problem if you don't even know an explicit analytic expression for the metric on the Calabi-Yau threefold? It's hard to even get started. Then there's the question of quantum corrections. So not everything in the computation is driven by quantum corrections, but it often matters what the string loop corrections and the alpha prime corrections are to some observables. And so these quantum corrections can control the vacuum structure. They can control the inflationary signatures. And the problem is one very rarely knows how to compute these effects past the leading loop correction. So that's also frustrating. What generally one has to do is use a very large number of approximation schemes that replace the problem of interest with a simpler problem where an approximate solution can be given, and then you make some sort of inspired matching that attempts to arrive at a believable answer for the full question. Let me give you a sketch of the state of the art in one corner. So I'll describe what the state of the art is in type 2B string theory on an oriental fold of a Calabi-Yau threefold. And this is, I'm really showing you where the bodies are buried and for a reason. The reason is I would like to point out where we could most use technical progress, where we would profit most from actually confronting the hard calculations and improving them such that everything could be totally explicit. Okay? So here's where things are hard. So you can specify a compactification at the level of some Hodge numbers and some orientifold actions and configurations of d-branes. Then what one generally does is assume that generic choices of quantized three-form flux leads to stabilization of the complex structure moduli and the axiodilaton. By the way, I should say it as an aside, for those who are not much involved in flux compactifications of string theory, I'm going to leave this discussion in a minute. I just want to give a sense of what the issues are, and we'll go back actually to field theoretic discussions. So the things highlighted in purple are the things where I think one could do better. So we assume that generic three-form flux stabilizes the complex structure moduli. It's a very plausible assumption, but one would like to be able to do the calculation in interesting cases. Then one computes the potential for the remaining fields, the Kahler moduli and the positions of d-branes. Not the full potential. You compute parts of the potential, the parts that are accessible, including contributions from, for example, Euclidean branes. But when you compute some effects on Euclidean branes, there's an arithmetic genus condition that determines whether there's a Euclidean d-brane contribution to the superpotential. And this is occasionally checked. One understands some general principles here, but it's not always checked in explicit constructions. A non-perturbative superpotential term from Euclidean d3 branes has a Pfaffian prefactor. It'd be nice to be able to compute that. It's a one-loop determinant corresponding to a threshold correction, effectively. That's a moduli-dependent term. It's an important contribution to the potential for the moduli fields. You'd like to be able to compute that. Usually we can't. So we model it as some order 1 function. We know some Elford-Brown corrections, but not all. So we estimate the scale of the remaining ones. We know some string loop corrections in some very simple cases, and we guess what their form is in more general cases. Now, with all that information, you have an effective action, or a model of what you think the effective action is, your guess as to the effective action. And this is something which could be improved systematically. Just do more computations here, more computations here, more here, more here. It's totally straightforward, it's just very hard. So with that effective action, then you try and figure out whether the theory admits interesting cosmological solutions. So you start out by trying to find vacua. Not inflationary solutions with dynamics, but ADS vacua or de Sitter vacua. So those vacua are local minima of the moduli potential. You have an effective theory, it has a potential energy function, you try and find local minima. Well, that's awfully easy if you have only a few moduli. If you have a lot of moduli, it's not so easy to find the minima numerically. And the critical points, which you can find, often are unstable. So in many moduli cases, the potential instabilities are very often grossly underestimated. And then you argue somehow for the possibility. Let's imagine that in this case we're starting with ADS4. For the experts, I am oversimplifying. There are other possibilities, but I want to give one line through a possible set of constructions. So suppose you start with ADS4, which is either supersymmetric or non-supersymmetric. To build a model that's cosmologically interesting, you need to increase the vacuum energy to positive values, and then you need to introduce some sort of supersymmetry breaking terms. So that could be done. Let me not go into that in too much detail. And then after all of that, now you have a de Sitter vacuum. You would like for this not to just be an isolated vacuum, but to be some sort of effective theory that can support inflationary dynamics. So you find a remaining modulus field, call it an inflaton candidate, and you try to compute the potential for that field. And you can't just do a leading order calculation. You have to do a subleading order calculation to make sure that corrections to the inflaton potential don't spoil inflation completely. So there are a whole range of ways in which those computations could go wrong. I'll just flash them here, but I won't describe them in a great amount of detail. So where does this bring us in terms of a status summary? What we have now, as Eva very clearly explained, is a lot of mechanisms for inflation in string theory. And I would like to sharply distinguish a mechanism for inflation in string theory from a concrete explicit model of inflation in string theory. So what is a mechanism? It's some scheme wherein you can identify a field or a set of fields and some terms in the potential, and an evolutionary process whereby those terms drive an inflationary phase, and they're plausibly not affected by couplings to other sectors that you don't know very much about. That's a mechanism, and we've got a lot of these. We've learned a lot about these in the last decade or two. And a number of these mechanisms have been shown to be perfectly compatible with moduli stabilization. But what we still don't have is some sort of end-to-end computation that's absolutely explicit about everything, and in which the subleading corrections that could potentially be dangerous have actually been computed and shown to be small, rather than being estimated to be small on scaling grounds. Now, that's not to say that anyone really thinks that all models that exist will be spoiled by these corrections. Not at all. I certainly don't want to imply that. I think a very large fraction of attempts to construct explicit models would eventually succeed once one became strong enough to compute these next order corrections. But we should bear in mind, these have not been computed. So this is part of the process of systematic checks and of figuring out what the theory errors are so we can know how well we really understand the predictions we're making, for example, in the NSR plane. The thing to keep in mind, though, is so I'm taking a deliberately pretty pessimistic view here because I want to highlight the nature of the interesting challenges. Okay, but the fact that there are challenges is not an indictment of the field. Progress is being made, and we've gotten fairly sophisticated at determining the action indirectly. And I think progress is clearly going to continue quite rapidly. But one should be aware that these computations are not, they're not cut and dried computations in most cases. Now, let me highlight something that Eva also mentioned, which is that there are string theory constructions of large field inflation mechanisms and of small field inflation mechanisms. And it's outrageously early to try to say which of those things is more generic in string theory. First of all, we haven't the slightest idea whether the compactifications of string theory that we understand now are representative of the full set of vacuum solutions of the theory. Even if we knew that was the case, we don't know whether we found most of the inflationary constructions in the set of vacua that we do understand. So it would be silly to try to make a prediction about which thing is easier or harder. What is clear, though, is that the technical challenges involved in realizing these two are different. Okay, you can try and quantify harder or easier in the two cases, but it's clear that they're different. Different issues arise, and that's why it's essential to build both types, not just because nature could turn out either way, but because we learn things from building both kinds of models. So if you have any interest in a broad summary of this, Daniel Baumann and I wrote a book about it, which we posted on the archive. So we put down everything that we know about what happened before BICEP and a little bit about what happened since, but didn't attempt to keep track of all the theory developments since then, which have been unbelievably quick. Okay, so in the remaining half of the talk, I'll tell you about a specific scenario. Starting out still a little bit general in field theory and then zeroing in on a particular string theory realization of large field inflation. Okay, so this is a model of Axion inflation. That's what I'll talk about. So what I've been mentioning so far is that one needs some sort of symmetry structure in the ultraviolet theory that can protect the inflaton potential. And a very natural proposal due to Friis, Freeman, and Olinto from the bottom up in effective field theory is that the symmetry that protects the inflaton could be a Peccei-Quinn shift symmetry. Phi goes to phi plus constant. The canonical Lagrangian that arises in that case, and we'll have a lot more to say about this shortly, has an axion, a kinetic term for an axion phi, and then a cosine potential for phi over f, where f is a quantity with dimensions of mass, and lambda is a dynamically generated mass scale. So this is a great EFT. It has very nice symmetry structure for giving rise to inflation, and we'll just ask about embedding this in string theory and seeing what we can learn. And I'm going to be pretty insistent that we keep trying to push up against the constraints from the UV completion in order to learn from them. So axions arise in string theory from the integrals of p-form potentials analogous to the one-form potential in electromagnetism over p cycles in the internal space. So here are the Ramon-Ramon p-form potentials and the NS-NS two-form potential. And in a typical Labial compactification, you can easily find hundreds and hundreds of axion fields. Now, in the absence of fluxes and wrapped branes, axions enjoy a shift symmetry to all orders in perturbation theory in the string coupling and to all orders in perturbation theory in the alpha prime expansion. And only non-perturbatively is the axion potential lifted. The non-perturbative effects break the continuous shift symmetry to a discrete shift by generating a periodic potential, which looks like this. So here, if theta is a dimensionless axion with period 2 pi, then the non-perturbative potential like this breaks, before non-perturbative effects, theta goes to theta plus constant, where constant is not quantized at all. And after the introduction of a potential of this form, the periodicity becomes 2 pi for the dimensionless theta field. And then if you think about it, this periodicity is determined by the kinetic term, really. This is the periodicity of a dimensionless field. The periodicity of a physical field with canonical kinetic term here can be obtained by rescaling the Axion kinetic term. So most of the remainder of the talk will have to do with this rescaling from the kinetic term for a dimensionless axion theta with some parameter with dimensions of mass, f, sitting out front, into a canonical form like this. There's actually an interesting result hiding in there. Now, what is this parameter f that appears in the kinetic term? So to relate the periodicity of a dimensionless field to a physical periodicity, you need to write down a Lagrangian with mass dimension 4. So if it's going to involve some d theta squared, there needs to be some quantity with dimensions of mass squared sitting out front. Where does this come from? Well, if the axions are coming from integrating p forms over p cycles, then you just dimensionally reduce the 10-dimensional action. And that gives rise to a kinetic term that's determined by the integral of omega p, if that's the p form, wedge star 6 of omega p. In other words, the metric in the internal space determines the kinetic term for the axion field. In a supergravity theory, this information can be packaged in the form of a Kahler potential, but neither this detail about axions from p-forms nor this detail about axions in supergravity is really relevant. All that's relevant is that if one does a computation in a more complete theory, one finds a quantity f, which is known as the Axion decay constant, and that can be determined in terms of the ultraviolet theory's data. So a very natural question is, can we just build large field inflation in string theory following precisely in unmodified form in the tracks of the Friis-Freeman-Olinto proposal? So that proposal was to take f much larger than m Planck, about 10 m Planck works. In that case, the cosine has such a long period that if you move up with even a small amount, you can drive large field inflation on the way back down to the minimum. That's the original proposal. Well, you need f much bigger than m Planck. And that should raise some alarms because this field here has period 2 pi f. So if f is large in Planck units, that means that there's a basic field whose fundamental period is many Planck units. And that, it raises alarms because it seems to be in tension with general expectations about the scale of symmetry breaking effects in quantum gravity. It's not a theorem at that level, but it seems something that's worth examining more closely. So how do you examine it more closely? You actually compute in string theory what these decay constants are. So you take some compactification manifold, you compute omega wedge star omega, integrate it over the internal space, and see what you get. Well, Banks, Stein, Fox, and Gorbatov wrote a very interesting paper about this in 2003, where they pointed out that the Axion decay constants in units of the Planck mass, in all presently computable limits of string theory, scale like some non-negative power of the string coupling divided by some non-negative power of a volume. How many powers of the string coupling appear there depends on what kind of form it is. For NSNS forms, alpha is 0. For RR2 forms, alpha is 1. And what power of the volume appears there depends on the dimension of the depends on the nature of the field, whether it's a 2-form or 4-form or 3-form or whatever. Okay, but the general point is that in the weak coupling and large volume limit, these decay constants are small. So what can you do? Well, if you would like, nevertheless, to realize a model of natural inflation in string theory, you ought to relax one or more of the assumptions that was implicit in what I said so far. So one obvious but very hard thing to do is just to say, well, the problem is that the decay constants are small at weak coupling and large volume, so let's just work at small volume and large coupling. Well, both parametric expansions fail there, so it's a hard task. There are some suggestions about how one might try and do that, but there's no sharp progress yet, I would say. Another very general mechanism, which Eva quite clearly explained, is to incorporate monodromy of an axion. Namely, to take an axion with a fundamental period that's sub-Planckian and traverse it many times, building up a super Planckian excursion. I'm not going to say a great deal about that more, a great deal more about that here. as we've already heard about it. But one should bear in mind that that effect can be combined with effects A and C. So effect C is just to consider more than one axion at a time. So if I have multiple axions, two possibilities present themselves. One is a particular kind of alignment pointed out by Kim, Nilles, and Peloso, which is if you have two axion fields with a fine-tuned relationship between their decay constants, then an appropriate linear combination of them can effectively have a large decay constant. Okay, so that's worth looking into. What I will be focusing on in this talk is called N-flation. And N-flation is a scenario in which you have a large number, you can have in mind hundreds of axion fields, without fine-tuned decay constants. The decay constants are what they are. And a collective displacement of many axions at once has an effectively super-Planckian displacement. Okay, so this is due to Dimopoulos, Koshru, McGreevy, and Wacker, 2005. So how does N-flation work? The basic starting point, which I'm going to question momentarily, is something like this. You have a sum for I equals 1 to n, where n is, again, let's say 200, of canonical kinetic terms. Oh, sorry about, I may be mixing sign conventions. You should always assume that all my kinetic terms are non-ghost type kinetic terms. So in the conventions of the rest of the talk, there's probably minus a half d phi squared, minus lambda to the fourth times a sum of individual cosine terms, each axion appearing in its own cosine term. Now, just to get intuition for what the proposal is, let's consider a case in which the axions have equal masses and equal periodicities. So if the masses are all the same, so expand the cosines, right? You get a mass term. The mass is lambda I squared over fi. Let's imagine that all the mi's are the same, all the fi's are the same. What you can define then as a collective field, phi squared, which is the sum in quadrature of all of the individual fields. And then the potential for that field v of big phi is just 1/2 m squared phi squared. And then here's the whole proposal is just this, that the displacement of the collective field is the sum in quadrature of the displacements of the individual fields. It's the Pythagorean sum of the possible displacements of the phi I. And if you have n fields, then the Pythagorean sum of n equal displacements delta phi is square root of n times delta phi. What does that buy you? Well, that means that if n is, let's say, 400 or something like that, and delta phi is a half, delta little phi is a half, then you can get a displacement of 10 m Planck, which would be sufficient to drive large field inflation. Okay. So it's in a certain sense living on the margins, in that it doesn't give you it gives you a large number, square root n, if you pay a topological price, right? You're dialing in that the manifold has very complicated topology, a lot of cycles, and then you win by a factor of square root n. The reason that that's not crazy is twofold. One is you don't need that much of a factor. The decay constants don't have to be way below the Planck mass. They just can't be 5 m Planck or 2 m Planck or something. They should be just a little bit below m Planck. And the second reason is what I started out mentioning. There are a lot of axions in typical compactifications. One is not going to extreme cases to find models with large n. Okay. But what I'm going to do in this talk, so it's actually, this is the scheme in N-flation, and the point of the remainder of this talk is that the situation is much, much better than this.
I thought they said it was reverse in the sense of the renormalization of Newton's constant.
It is certainly. So there's a renormalization of the Planck mass, which is proportional to chi and the Euler character of the compactification. And if that's 0, then there's no correction. If chi is small compared to n, then it's parametrically not as good as square root n. No. If chi is small compared to n, it's parametric. It just doesn't scale like square root n exactly. Right. Yeah. So there's an additional topological choice. You have to build in that n is big and that chi does not scale like n. And you have to build in that all of the and I think the major question about N-flation, aside from the ones that I'll be raising and addressing soon, is whether all quantum corrections to the Planck mass scale with chi. And that's not a point that's yet been checked. Have I addressed your question about the parametric scaling? Oh, yeah. Okay. So I'm going to come up with a rather different result than this Pythagorean sum that arises here. Okay. So, and it's different in a useful way. It's going to be easier to embed the construction that I will describe in a compactification. The constraints from Planck scale physics will be milder than the constraints are in this sort of default case that was originally proposed.
The bold phi there?
Yes?
It's not canonically normalized, right?
Is
that right?
Is that?
Well,
Yeah.
so usually when you talk about the Lith bound, you have a canonically normalized scalar, but the capital phi here, I mean, it's not going to be canonically normalized, right?
Why not?
Well, because it's a nonlinear function of the phi i's. It doesn't matter. You'll show how.
So
it goes.
the kinetic, this is the kinetic term, and so yeah, so the collective field that we'll be describing will be a field with canonical kinetic term. In fact, it's only a single. In the end, it's only going to be a single one of the phi's that's evolving. Yeah. So, in fact, the kinetic term is the primary question, right? So this is not this assumption that one should really just superpose them precisely in quadrature like this, and that the masses are all equal and the decay constants are all equal is sort of the problem. Okay, so what I mean by that is, in general, if you have a kinetic term like this, but the different decay constants fi are distinct, so let me just order them. F1 the smallest, Fn the largest, and let me take Fn to be less than m Planck. If you want to have a figure, imagine that Fn is a half m Planck or something like that, and F1 is some ways down below that. Okay. A question you can ask is, what's the diameter of the canonically normalized field space? So I think I just expressed this in a clumsy way here. What we're really interested in doing is asking the question, what's the diameter of the canonically normalized field space? That really is the sum in quadrature of the individual diameters. Okay, so that's really the right thing to say. So yeah, forget this expression here. This one is in fact a correct expression, and this one is the one that enters the life bound. Okay. And note in particular that there aren't any missing square root n's in this definition. So what happens if the fi's are distinct? So then the diameter of the field space, this is not necessarily the range over which you could usefully build a model of inflation, but the actual maximum diameter you can go before you come back to yourself via a periodic identification is the Pythagorean sum of the f's in this model. It is. Okay. And the Pythagorean, I'll just call it f sub pi for Pythagoras. And in general, if the f's are rather different from each other, then the Pythagorean sum is nowhere close to square root of n times the largest of the f's. Okay. In a sense, all the axions with quite small f, smaller than the biggest one, are effectively wasted. They don't contribute in a useful way. It doesn't scale parametrically with n. It scales parametrically with the number of axions that are almost Planckian. Okay? And that's what I'm going to fix. The reason one would want to fix it is the whole problem is making an axion decay constant almost Planckian. This is very different. Making it super Planckian, we don't know how to do for individual axions. Making an individual axion decay constant a 10th m Planck, a half m Planck, is hard work because you have to go toward a boundary of the moduli space. Now suppose you want to do that for two axions at once. In a certain sense, you have to go toward two boundaries of the moduli space. You have to be approaching sort of a corner in the moduli space. Then you want to do it for three axions. You have to keep doing it. And you end up in a really, really strained regime where perturbative control is virtually impossible. So one really should not extrapolate from an example with small n, where the decay constants can be found to be, I don't know, a 10th m Planck or something like that, and say, well, why don't I just scale that up at large n? I can win by a factor of square root n per this estimate, and surely in the example with large n, I can also get all the decay constants to be about a 10th m Planck. That's not achievable in my experience. So I'm going to fix that problem in the following way. The point is that we have to pay careful attention to the kinetic term itself. So on totally general grounds, the action for n axions at the two derivative level and at the level of single instanton contributions to the potential takes this form. Now here, this kinetic matrix Kij is just some symmetric matrix. In n equals 1 supergravity, it'd be a Hermitian matrix, but let's leave that aside. Okay, this matrix is not automatically diagonal when the potential takes this form. So let me explain that in some detail. What do we even mean by an axion decay constant in a two-axion system or an n-axion system? So here's a single axion system. F is just a parameter with a scalar parameter with dimensions of mass, and then you can absorb by the redefinition phi equals f theta and write the Axion Lagrangian in the canonical form like this. All right, so suppose you're in an n-axion system that, and this is totally non-generic, but suppose the Axion Lagrangian has a form like this, where when the potential, in the basis where the potential looks like this, the potential is a sum of, the kinetic term is a sum of individual terms. Then you just repeat the same game n times, you get n copies of the original Lagrangian. That was the starting point for the N-flation discussion. You could do that. But the question is, if there are mixings in the kinetic term, if the kinetic matrix is non-diagonal in the basis in which the potential is a sum of individual cosines, what happens then? So you may think, wait a minute, this is somehow trivial. I should be able to get rid of this by a coordinate transformation. No, you can't get rid of it by a coordinate transformation because the coordinate freedom has been fixed in the following way. The naive field space before any periodic identification, just at the perturbative level, before any non-perturbative effects, is just Rn. And then the identifications theta I goes to theta I plus 2 pi define some lattice in this space. So imagine there are n instanton contributions, and associate one axion to each individual instanton contribution. Call each of those axions theta I equals 1 to n. And without any loss of generality, you can take each of them to have period 2 pi. Okay? So that means that the naive field space was Rn before identifications. After Rn, it's a hypercube in Rn of side length 2 pi. And that defines a preferred basis. That's the basis on which the potential is a sum of individual cosines. If you rotate, for example, to diagonalize the kinetic matrix K, then the cosines will become cosines of linear combinations of the phi fields, of the theta fields. Okay, in a certain sense, you may say, so what? So why not just deal with it and rotate this kinetic term and then have a cosine of a sum of things? Well, I'll show that actually one can do. There's a missed opportunity here to get an additional factor of square root n scaling in the field range. So let me just define terms. The lattice basis is the basis in which the potential takes this form, in which the dimensionless field space is a cube. And the kinetic basis is the eigenbasis of this matrix Kij. Okay. So of course, these are just not the same thing in general. Okay, if you don't believe me, well, I hope you believe me. Does anyone not believe me? I can give you some examples, but it should be obvious, right? I mean, to say that these things are generally the same, the lattice basis and the kinetic basis, is to say that generically axions just don't experience any kinetic mixing, which is just wrong. In all the string theory examples we know how to construct, you can easily work this out, and you don't find, it's terribly hard to find examples that don't have significant kinetic mixing like this. Okay. So now, what do you do with it? What we're going to do is we're going to start from this general form and be careful about the kinetic mixing and see how that helps with the field range. So the mechanism I'm going to be describing, the motivation for this came a little bit from string theory. In particular, the idea of N-flation was strongly motivated by string theory considerations. But the kinetic alignment mechanism that I'm going to tell you in the remaining few minutes is not a string theory specific mechanism, it's just a fact about field theory. It's a fact about simple field theories. This is not going to solve all the problems of N-flation. It's not going to solve the renormalization of the Planck mass we heard about, but it will alleviate quite a few problems. So here's a diagram that shows the whole solution in its great triviality. So the white square is the naive field space. The field space, I'm going to draw an example with n equals 2 here. So here's theta 1 and theta 2. So this is the naive field space, outline square. And then what the metric information does is it tells you how to associate to naive dimensionless displacements, delta theta, a meaningful physical displacement with dimensions of mass. That's the utility of a metric on field space. And so let's imagine that our metric on field space has two eigenvalues, f1 squared and f2 squared. And let's consider two situations. Situation 1 is the one in which the metric on field space, this Kij, is actually diagonal in the lattice basis. Okay, in that case, the metric eigenvectors line up with the edges of the square. And what the metric does is it tells you that a dimensionless cube, dimensionless square here, gets squashed into a rectangle of side lengths. I think I've labeled this wrong. This one's actually f1 and f2, with diagonal 2 pi square root of f1 squared plus f2 squared. So that's the trivial case. Of course, the generic case is the one in which the metric eigenvectors don't exactly line up with the edges of the square. And there's an optimal version. Okay, so I'm going to describe the optimal version first, and then I'll explain to you why the optimal case virtually always arises. Okay. So the optimal situation is the one in which the particular eigenvector of the metric that has the big eigenvalue happens to line up with the long direction of the naive field space. That's advantageous because the metric is a rule that takes units of displacement in the naive field space to units of displacement in the physical space. And so what you'd like to do is take the longest direction in the naive space and count those directions most in terms of physical space. So that's depicted here. So in this case, the distance from the center to the corner is square root of 2 times pi f2. And if this were an n-dimensional case, it would be square root of n times pi fn. Now, if what I had to do to make that happen was make some horrendous alignment such that I fine-tune my effective theory to make one particular eigenvector of the metric line up with one particular direction, then it would be a pretty horrible way to solve any kind of problems. Okay, and the thing that's interesting about this is that this is essentially, this kind of alignment here is essentially unavoidable. Not only is this case non-generic, but this case is this. You might have naively thought, well, okay, this isn't generic, some intermediate angle is generic. No, actually the generic case is that the alignment is almost perfect with a long direction, and so let me just explain that. It comes from pretty simple geometric considerations. In Rn, you have n basis vectors, and there are 2 to the n hyperoctants. Okay, so and you've got a long diagonal of a hypercube going along each of the each of the centers of the hyperoctants. And so if you just draw some vector at random from some rotationally invariant distribution and ask, with which of these, the basis vectors and the hyperoctants, does it have its largest cosine? Well, almost surely it's going to have its largest cosine with one of the vectors running down the center of a hyperoctant rather than with a vector running down the side of a cube. Okay, this is just a stupid point that there are more diagonals than edges in this basis region. Okay. At large n. Okay. There's a factor of a half. I mean, there's no difference here, obviously, because in fact, the number of lines is half the number of hyperoctants. So here, 2 equals 2. But at large n, it scales differently. So the result is then that if the eigenvectors are uniformly, even close to uniformly distributed in angle, then at large n, the statistical distributions of the components, so here I is the ith component of some eigenvector a, so a is the 8th eigenvector. The statistical distribution goes like 1 over square root of n times a normal distribution. And so that tells you immediately that it's fantastically unlikely that the eigenvector components will fluctuate upward such that one of the components is almost 1. Okay. In other words, for it to be along a side, it has to be approximately 1, 0, 0, 0, 0, or some permutation of that. That's improbable because all n minus 1 of the other components had to fluctuate down. So you can quantify that. And that means that generically the diameter of the field space is quite close to 2 pi fn square root of n, which is a lot bigger than the Pythagorean sum. That means that the axions that had small decay constants help us just as much as the one that has a big decay constant. They're still around helping. Okay. There's actually, I think, a rather nice and richer way of understanding where this comes from, although this really does suffice in a certain sense, which is that if the Kahler metric, the kinetic matrix, or more generally the Kahler metric, is a member of some rotationally invariant matrix ensemble, for example, the Wishart ensemble constructed by taking the transpose or Hermitian conjugate of a matrix A and contracting it with A itself, taking the entries of A to be stochastic variables drawn from some statistical distribution omega with variance sigma squared, then one finds a phenomenon which random matrix theorists refer to as eigenvector delocalization. And eigenvector delocalization is just the statement that the eigenvectors, to good approximation, have components that go like 1 over square root of n times something that's order 1. Okay. So this fact is generally checkable. Some inspiration for thinking about things this way comes from trying to be a little bit more precise about how this could arise in actual string theory constructions. So what I'm effectively getting at here is that we would like to model the Axion decay constants for what they are, which is eigenvalues of the Kahler metric. So you'd like to know, is there some sort of ensemble description of Kahler metrics in string compactifications? So can you write down an ensemble that describes the properties of the metrics on moduli space in some class of compactifications? We don't have an analytic result for this. There's some work in progress. But this is something that you can address empirically by just building an ensemble of Calabi-Yau threefolds numerically and assessing what the eigenvalues of the metric look like. And here's one example. So here, this is a spectrum of eigenvalues of the Kahler metric, i.e. a spectrum of decay constants f squared. And you see, for a case where n is equal to 15 here. So this is h11 equals 15. And you see there's a lot of spread. So this is fn here, and this is f1. And you see that square root of n fn is going to be an awful lot bigger than the Pythagorean sum of these. So we're working hard to try to come up with more precise versions of this, but that's still a little ways away. Okay, so let me summarize and then conclude. So there are some challenges in N-flation, a bunch of challenges. One challenge Eva already brought up, which is the topological choice. You need to, first of all, you need to be starting in a scenario with large n. Then you need to arrange that there isn't a large renormalization of the Planck mass. So that requires a choice of n and a choice of chi. Then you need to get many large decay constants in the standard formulation. Large meaning not super Planckian, but a half m Planck, a tenth m Planck or something. And then there's the worry about the evolution of the fields that are partnered with the axions by supersymmetry. And then there's the question of setting up the initial conditions. And what we find is that the problem of many large decay constants is just very strongly alleviated. It's transformed, really. And then the problems of Saxion evolution and the problem of initial conditions are modified in some ways. We're not, I think, at this point ready to say that we have definitive improvements, but the nature of those problems is slightly changed. And the problem of topological choices is not changed in any way. Okay, so let me conclude. Mostly I'm going to conclude about the general remarks, not about this particular kinetic alignment thing. So evidence for primordial gravitational waves allows us to probe symmetries, in particular shift symmetries of inflatons coupled to quantum gravity, by pursuing explicit ultraviolet completions of inflation. And at this point, we understand string theory mechanisms both for large field inflation and for small field inflation. It's important to recognize that by now, despite all of my complaints about the need for technical advances, it really is the case inflation in string theory has advanced to a stage where the theory errors can be quantified and models can be falsified. And that's already happened in many cases. So that's exciting. But really painstaking work is required to characterize any given model well enough to actually run up against the quantum gravity constraints, if any. In this N-flation example, the next quantum gravity constraints one would like to understand come from subleading alpha prime and string loop corrections to the effective action that might produce additional renormalizations of the Planck mass. So much work remains to understand even the models that have already been published, and yet more work to map out the space of models that could exist even in known compactifications. And then unimaginably more work to map out the broader space of solutions of the theory. But as Eva was stressing, even though we have a vast number of vacua, a very large number of effective theories arising, it's quite clear that there's a lot of structure. And the way we can learn and profit from this is by actually exploring that structure rather than assuming that there aren't any structural constraints. So I argued that axion inflation is one of the most promising routes to large field inflation in string theory, and showed that in the specific context of N-flation, just one of quite a number of ways one could realize large field axion inflation in string theory, we can make the model work a lot more easily using a totally generic phenomenon of kinetic alignment, which then allows you to build a model in which only one axion decay constant is largish but subplanckian. Thank you.
Okay, any question? No questions? So I have one. So this was about UV completion. So you didn't mention towards the end, but you want to know really there are examples of genuine string compactification which actually realizes, and this scenario. And so with your statistical analysis of the actual Calabi-Yau compactification, do you have series of examples to that effect?
No, and the examples are far away. What we're really trying to, so the pressure pushes sort of in the opposite direction. The statistical analysis is driven by the essentially obvious idea that some things are actually simpler at large n. And by working at large n, you can render yourself partially protected against non-structural constraints, but in a sense, stochastic variations in the microphysical information. For example, this information like this, the distribution of the Wilson coefficients or something like that. The problem is in exactly the regime where the random matrix descriptions are applicable. And actually, we understand a fair bit now about the Hessian matrix in supergravity in this context, although a little bit less about the Kahler metric. In exactly that regime, it's terribly difficult, even if you knew the full effective theory, to find a minimum of the effective theory, let alone to find most of the minima, just as a computational problem. And we're rather unsophisticated at these kinds of numerics, but even people who are much better at it have a difficult time finding metastable solutions in field spaces of this size. So I don't actually see much hope of giving you, the problem is for N-flation to work, you need realistically N of, let's say, 400 or 800 or something like that. And I can't foresee in the near future giving you an example of a Calabi-Yau where I actually find a minimum of the moduli potential. So the hope really is that by these sorts of approaches, this doesn't get all the way there. This tells you that you only need one axion to be big, and the remaining axion decay constants can be small. What I could imagine doing, though, is milder than a full construction, which is giving you a Calabi-Yau which has large Hodge numbers and in which one of the decay constants is large, the rest of the decay constants are sort of more modest, and I show you that I'm inside the Kahler cone and that all the corrections are small. That's foreseeable. We're on the path of that.
Okay. Any other question? If not, let's have a coffee break and meet again at 3:30.